Hello, everyone. My name is Rob Higuerita, and I'm a Principal Technical Account Manager at AWS, and I'm based out of Austin, Texas. Welcome to AWS Supports You, where we share best practices and troubleshooting tips from AWS. And here at AWS Support, we practically help you optimize performance, lower costs, and innovate on the AWS cloud. Joining me today is Juan Moreno from the AWS Specialist Organization. Can you give us a quick introduction, Juan?
Hi everyone, I'm Juan. I'm an Amazon Braket solutions architect. I'm also based in Austin, Texas. Thank you for having me, Rob.
Great, thanks, Juan. And today we'll be introducing you to Amazon Braket, the quantum computing service from AWS. We'll specifically focus on the security posture of the service. But before we do get into the details today, a quick note to the attendees online. Please feel free to use the chat window on the right-hand side of your screen to let us know where you're joining us from today and share your questions and thoughts throughout the episode. We really do look forward to hearing from you. So, Juan, we're going to be talking about Amazon Braket and quantum computing. So for me, I'm still very new to quantum computing, and maybe some of our audiences too. So I think it'll be interesting to, hear some definite new info for me, I'm sure, on quantum computing. And also, I'm really interested to hear about, the security side of it. So looking forward to things today.
It's a common thing. There are many people who are new on this, especially for both people who, like me, who come from the computer science side of things and suddenly discover that there is some weird interconnection between science and technology, and it's a very different service. So hopefully today we will shed some light on some of those things, and we will for sure cover the security aspects of it as well.
Great, yeah, I'm sure I'll learn something, and I'm hopefully the audience will learn something. So I'll go ahead and turn it over to you and let us get started at going through today.
Perfect. All right. Thank you, Rob. So, all right. Yeah, as I said, it's better that we get a little bit of an introduction. For those of you who are new to quantum computing, what is that? How it's different from classical computing? After that, we will go into what AWS is doing in the quantum computing space, and specifically for our Amazon Braket service that I work with. We will go and try to see the architecture, how it works inside, and all that. We are going to then transition towards more security discussion. And I'm going to use identity and access management as an excuse to give you an idea what are the other services that Amazon Braket interacts with. And finally, we will be sharing some examples of scenarios that in my interactions with customers, we have seen that they are concerned about and they ask me about in terms of how to build a private environment, right? So we will cover all those things today, hopefully. As Rob said, please jump with your questions on the chat, and we will be getting them. So first of all, yeah, the million-dollar question, what is quantum computing, right? Well, you could think about it as a completely new paradigm of computation that is very different from everything we have done up until now, everything we've done in the past with classical computers. And the reason why it's different is because leverages different laws, the laws of quantum mechanics, that it can be very different to the laws of quantum physics, the classical physics, the physics of Newton that we are used to. So the reason why this is different is because the way these machines are built are also completely new and different, and the problems that you can tackle are very different. So problems that in classical computer used to take a long time or are completely intractable, now with a quantum device you are able to do it in a much more efficient way because of this new way of computation. Now, the limitation we have is that the machines or the fault-tolerant devices do not exist today. They are being built, but building one of those quantum machines is a difficult challenge from both the engineering but also the scientific point of view. It's difficult to build quantum computers. So you might be wondering, okay, so why are people talking about this? Why AWS is in this space? What is all the interest? So the problems I was mentioning before can get really hard and really fast. And as the number of variables, or as a result, the number of combinations increase. So it's not only that the cost of computation for a traditional computer for these problems can get really expensive, it's also that it takes a long time. So in this super ambiguous graph that I'm showing here, I just wanted to give you an idea of the scale we are talking about. If you could gather together all the computation capacity on planet Earth and put it together to work in a cluster, some of these problems still couldn't be solved. It could take maybe hundreds of years for some of them, while a quantum computer could do it in a fraction of the time. So this is why the quantum computing proposition is quite compelling, right? We don't know when it's going to happen or if it will happen at all, because we are fighting nature almost every step of the way while we build these devices. But definitely advances are being made, and this is a very exciting time to be on this field. I know I said a lot, so probably there was already some question in the chat about what I just said about this introduction. Is there anything there?
Hey, Juan, thanks for the little introduction there. Yeah, no questions right now from the audience. So, audience, please do post your questions here, especially if you've had experience with working with quantum computing. Even if you just want to drop a note that you've taken a look at Braket in the past, happy to hear about that. And yes, please make sure to post your questions. Just for my own sake, Juan, I'm curious, if I wanted to get started with Braket, is there like a free tier usage on Braket?
Yeah, there is. We'll touch a bit on the simulators later, but you can have simulation time 1 hour per month for free with the free tier. So not the quantum devices, the hardware itself, but the simulators can be used 1 hour a month for free as part of the free tier.
Great, thanks, Juan. I'm sure that'll be helpful. Just especially for me, if I wanted to get in there and try and use it, I would need that free hour to get off the ground. So,
That's right.
All right. Well, I'll let you continue through some more content here. Appreciate it.
Perfect. One thing that probably I want to say to wrap up with this slide is the type of problems I'm mentioning. People might be wondering, okay, what problems are those? Well, you shouldn't think of maybe a web server or a relational database or things like that. It's problems that are mathematical problems that grow exponentially in some factor, right? A popular example is the factorization of numbers, for example. That is the base of modern cryptography. So if you, for example, provide a traditional computer two numbers, a 3 and a 5, and you ask for the product of those two numbers, they will return a 15. And that's a very easy operation for a traditional computer. However, if you are for a machine, so instead of a two-digit number, you are talking about 600 plus digit number. That is where, for example, RSA 2048 is based on. Then the machine might take hundreds of years to make that calculation and bring that number back. And that's where cryptography is, how cryptography is used, right? This is also used for simulations, for example, molecule simulations. We have to do simplifications on very complex molecules because it's impossible to calculate all the energy states of things like the catalysis or protein folding and things like that. So the quantum devices have the promise to make those operations in a much more efficient way in a shorter time. All right, so let's talk a little bit about what AWS is doing in this space. I mentioned about Amazon Braket that I work with, but probably the first thing we need to say here is that we here at AWS are humble about the technological and scientific challenges, but also we are excited about their potential. And for that reason, we built an ecosystem or a number of services that cover every single aspect of quantum computing and quantum technologies. So first of all, we have the AWS Center for Quantum Computing. They are on the top left. This is a research center close to Caltech, the California Institute of Technology. And this is bringing together the world's leading quantum computing researchers and engineers. And they have a mission. The mission is to accelerate the development of quantum computing software, but also hardware. We also have a research program, the Amazon Quantum Solutions Lab, that allows customers to work with leading experts in quantum computing, but also in things like HPC and machine learning. What this team does is to work from the problem backwards with the customer in order to do benchmarking and build algorithms and help the customer to develop their own intellectual property and get them ready, in one word. We have a growing global community of technology and consulting partners that are specialized in different areas of quantum computing. They are an absolute delight to work with. They are really good at what they do, and it's there also for our customers who are interested in a specific industry use cases. And finally, Amazon Braket. That is the service that I'm going to start talking more in depth now. That is the single pane of glass where users can basically write their code and test their code and check different endpoints, quantum devices, simulators, and all that. So Amazon Braket, I'm going to show you in just 1 second in a small demo. Allows you to start building your code without having to learn about every specific programming language for every specific device. And all the devices, a variety of different quantum hardware is available in the console for you to use. So in that sense, we say that we are democratizing the access to quantum computers. There is an SDK, the Amazon Braket SDK, that is public in GitHub and you can download and start using. But we also have Jupyter notebooks where you can write your code, change your endpoint, and test different devices. Usually you start doing simulations, as I was mentioning before, on that free tier. You have different types of simulators that simulate the same behavior as a quantum computer. And you can start playing with those. And then when your code is ready, your numbers make sense, you can run your circuits in an actual quantum hardware or your annealing problem, depending on what type of quantum computer you want to use. And analyze your results and iterate. So you have to basically, you can spend your time doing and working on your problems rather than learning new programming languages and things like that. This is how it looks visually, Amazon Braket. On the left-hand side is you, the user. You have the managed notebooks, as I said. You don't need to use the console or the graphical environment at all if you don't want to. The actual IDE is, the actual SDK is available in the public GitHub repository. We'll paste some links there for you to download and use it. And from there, you can start writing. And you also have the console that I'm going to show you in a second, where you can see the status of your tasks, and the characteristics of the devices, and things like that. At the core of the service, we have the simulators there in the center of the screen. We have 3 simulators today, but the actual Braket SDK also comes with a simulator built in for very small prototyping that you can use for free if you want to. Usually, it's the best way to get started. Then in the quantum hardware, we have agreements with 5 different vendors at the moment. The last one you see on the list there, QEra, is not available yet, but it's coming later this year. But the others are available today for you to use. There are different types of technology. The first one that you see there, D-Wave, is an annealer device. It's a machine that is very well suited for optimization problems. And the others, Rigetti, IonQ, and Oxford Quantum circuits are based on superconducting, are based on gates, are universal gates. And again, I'm going to show you how the difference between them are and how do they work. Then on the right-hand side of the screen, we have integrations with the rest of the AWS services, right? You can set up alarms the same as you do with other services for CloudWatch. You can use EventBridge to send you notifications when a task is completed, or to hook it, maybe the results of the quantum computation, into a machine learning pipeline with SageMaker if you wanted to. You store the results of your experiments in text files in S3, and everything is encrypted end-to-end. And you can create specific policies with IAM that we are going to cover next, for restricting access to specific devices, or only give access to users to the parts of the service that you want to use. That's all available. All right. This is all good and nice. It's theory, but let's go and move on into a demo. I'm gonna show you how these things work in practice. Let's jump into the console. Here's the Amazon AWS console. You can just go and click on Amazon Braket if it's in your recently visited services. Otherwise, you can move on to do a search by the name of the service. Then you go to Braket, and here you have, first of all, the devices page. Here on the left-hand side, you can see that you have the notebooks as well, and the tasks and jobs. For every device, you see that there is a number of features or characteristics that are defined there. The number of qubits, that is the main building block of these devices. The qubits are similar to bits in the sense that they can also take the value of 1 and 0, like a bit, but they can also have the special properties of quantum computers like superposition and entanglement that I'm going to show you in an example in a second. Then you will have information of the region where they are stored as well, the availability, if they are online or not, and also you see there a time clock there, an availability window. Some of the devices are available 24 hours, some others are not. But that doesn't mean that you cannot run your code anytime you want. If the device is not within the execution window or the availability window, you can just send your code to a queue, and it gets executed within the next time frame. Let's go ahead and take a look to some of these devices. Here you can see additional information. As I said before, the availability is there. And then you have the number of qubits and the cost. The cost is as follows. You have the task and the shot. Because of the probabilistic nature of quantum computer, when you are writing a circuit, you just don't execute it one time, that circuit, and move on. These machines return errors. So also because of, as I said, the probabilistic nature of the technology underneath, you need to execute the circuit a number of times, 100 times, 1,000 times, up to 10,000 times with some of the devices. And those are the tasks. You pay per task when you use the service. And then we group all those tasks into, those are the shots, apologies. And all those shots get grouped into a task. So the pricing units are the number of shots that you execute for an experiment and the number of tasks for them. Here's the ARN. Like every other Amazon device or service, you have an ARN. And then this is the topology of the device. In this case, there's a next neighbor topology where the qubits are connected with the one right besides, forming this ring. And after that, you can check the calibration window that it will tell you basically technical data about the quality of your qubits and the fidelity of the gates that can be implemented with every qubit and every pair of qubits. This is useful information for certain circuits. Let's go ahead and go to devices. Cannot show you all the devices in the time we have, but let's click in another one for you to see the difference. We're going to move to the largest device that we have at the moment in terms of gate-based computing. That is the Rigetti device. It's 80 qubits, and this is the region where it is. And as you can see, if I click inside, the topology is quite different. The same information is there. This device is available right now. And you can see that there are also rings, but they're interconnected with each other in this way. It's a more complex topology. And as such, the calibration window is also more complex. Here you can see for every specific qubit, what's the fidelity of certain parameters. And also if you go to the edge specs, you can see for every pair of qubits, what is the quality for certain type of gates. This is very useful in this device because it's going to give you great flexibility when you are writing complex circuits to specify which qubits you want to work with and what is the type of gates that work better in which qubit. Let's go ahead and show you a third device. And before we move on into something else, that's the IonQ device. This is also a gate-based device, but it's based in trapped ion technology. So the way the qubit is built is different. As you can see here, this is 11 qubits that are connected in a ring, but the ring is connected in a full mesh. So all the qubits have an equivalent distance with each other. That has some good properties to build this way. And the calibration window as a result is simpler because the distance between the qubits is equivalent. All right, coming back to devices, probably the next thing is to touch on the simulators real fast. As I said before, we have 3 simulators, one with 34 qubits, other one with 50 qubits, and the noise simulator with 17 qubits. There are different types of simulators, but basically you could think about the first one, the SP1, the state vector simulator, as the more general purpose one. It will store the whole wave function, meaning all the possibilities of your problem will be stored and returned to you, even the very unlikely ones. And then you can use the tensor network simulator when you want to map your problem into a graph. This simulator will traverse that graph and gives you the better outcomes after an internal evaluation. And finally, the density metric simulator, or DM1, is made to simulate noise. You will be able to create a circuit and add noise to it in the same way that a real quantum computer would do in the real world. Let's go ahead and take a look to the notebooks. Let's write our first code. Creating a notebook is easy. If you are familiar with SageMaker, this is exactly the same. It's based on SageMaker, as you can see by the interface. You can go ahead and do that. It will take just 5 minutes or so to create a notebook. I'm going to skip that and go directly to these notebooks that are already created. The first thing you see when you create a notebook is this Braket examples folder, and inside it, you will see a lot of examples for you to get started. If this is all new to you, you can go to the Getting Started folder. That is what we're going to do today. But you also have more advanced programs like the Grover search algorithm or the optimization problems, also quantum machine learning problems where you use a classical computing and quantum computing working together. So you have all those examples available for you. Okay, so here in the examples, I'm going to go to the QPU access so you can see a real quantum device working and giving you results. What I'm doing here, first of all, is to import a few libraries, math libraries like NumPy and things like that, and then the proper Braket libraries that are going to allow me to write my circuit. And then after that, we can check what is the compatibility in terms of gates for my device. By running that cell, what I'm doing is asking all the devices available what gates are supported. And you can think of the gate in the same way that you will think in the classical world, right? Like 50 or 60 years ago, when classical computers were starting, there were no high-level programming languages. We're in this stage as well. So we are just basically writing our circuits, putting a series of gates in series and executing the circuit and reading the results. Literally the ones and zeros in the final readout. The difference is that the sum of the gates are different because, as I said, they are leveraging the laws of quantum mechanics. So we will have special properties that we're gonna see hopefully in this example that I got here for you. In this picture, you see a representation of a 2-qubit circuit. It has 2 qubits. They are both initialized to the value of 0. And in the first one, you see the Hadamard gate being applied. That's big square with an H means the Hadamard gate, and it's going to bring my first qubit to a superposition of states, which means that while the computation is happening, this qubit has the same probabilities to return a 0 or a 1 in the final readout. So chances are equal. On top of that, in my second qubit, I'm going to make use of the property of entanglement in quantum computing between two particles or within a quantum system, in which basically I'm using a control NOT gate. That's that square with that black dot that you see there, in which basically I'm subjecting the result of my second qubit to what I obtain on the first one. If the first qubit returns a 0 as a result, the second qubit will not change, and as you can see, is initialized to 0 as well, so it will return a 0. However, if the first qubit ends up being a 1 as a result, the second qubit will also change and it will turn its value into 1. So what this means is, under perfect circumstances, I will always get, as a result, when I read the result of this qubit, a 0 and a 0, or a 1 and a 1. So how do I write this in Braket? I just need to define a circuit, as you can see there. I call it bell because this is called a bell pair. I write circuit and I append my gates. I append both gates, the CNOT gate, the Hadamard gate and the CNOT gate, and I execute it. With that, I only have just the graphic representation of it. Now I need to attach a device to run my circuit. And this is when things can start to get more interesting. First of all, I use the local simulator, as you see here. I define it using this device variable, and then I just count the results and the number of times that I'm returning one result or the other. And I plot the results. As you can see here, almost 50% of the times, I'm obtaining the 0, 0 results, and 50% of the time, the 1, 1 result. After that, I can start basically either using the simulators, and now for the sake of time, I'm going to go ahead and use a quantum device. This is the device that I showed you earlier, of the 80-qubit device from Braket. And we are basically writing exactly the same code, but the only thing we are doing is changing the endpoint, as you can see on that cell on the very top. I'm defining the Braket device, putting the ARN of it, and the rest of the code doesn't change. Basically, I'm just changing the endpoint. I collecting a few more results, but that's about it. I'm checking the state that goes into created state as soon as I do it. And then I can check again for the state of my task, and it's now in the running state. While that's running, I can go ahead and go to another device and run the same code. This time I pick the trap ion technology from IonQ, change the ARN, and using exactly the same code once again, I just decide how many shots I want to do in the machine. In this case, I set 1,000 shots and see what's the status after creation to make sure that everything is okay. As you can see here, this goes into queued state. What that means is that maybe right now the machine is busier, there are more people executing code, so my circuit, even if the device is available, is in queued state. After a few minutes, if you're in the availability window, or after a few seconds, you will get your results back. And that's the other important piece, right? From here, you have the possibility to work with your tasks. You can either go to the console or do it here by code. Here, the only thing I'm doing is to query the API using the SDK and asking for what's the status of my task. First of all, for Rigetti, here, as you can see, the task is now completed and I get all my results back. And check this graph. This is interesting. If you compare it with the previous one, the local simulator, I had a perfect superposition and entanglement, and it was 0, 0, 1, 1. However, here I see appearing other counters that we didn't have before, 1, 0, 0, 1. This is just due to the normal noise that these devices have nowadays. We have to account for it in our calculations. And this is a good example of how a real quantum computer operates, returning these mixed results at times. I can do exactly the same thing, recover my task from the IonQ device and see if it finished already or not in the same way. As you can see, the code is identical. I'm just representing the information. But this one is queued, so we are not going to see it finished for now. But what we can do is to go to the console for this one in IonQ and see how is it doing, basically. This is the queued status there. And then if you click on the task, you can see the more information about it. It was 1,000 shots, as you can see there on the right-hand side. You get all the ARNs for the device itself, for the task itself that will allow you to recover it. And there is a placeholder there, as you can see, for the S3 bucket. When the task is finished, you will see a link to S3 that you are able just to click on, and it will take you to a results.json file that you can open, and you will see all the details about your task, the number of qubits, how long it took to execute, and all the how the machine rewired itself in order to execute your code. It's very, very detailed information. And again, you can use that file to feed it into somewhere else. Okay, I think that's all I wanted to show you for this demo. So let me know. Is there any question there? So far, so good.
Hey, Juan, thanks. Thanks for all the info. I think it's really interesting how you were showing that you can have the same code run against the different hardware and kind of make it easy for people to, or not easy, but at least makes you don't have to rewrite everything for every device that you're using there.
That's right.
We did have a question that came in a little bit earlier in your presentation from JibJab06. JibJab06 wanted to know, does the AWS Center for Quantum Computing publish example data to use for learning quantum computing, or are there examples provided?
Yeah, so that's a double answer for that question. Thank you, Rob. So first of all, for the Center of Quantum Computing, they do have publications and they produce papers about their advancement on their work. So there are some interesting papers if you head to the AWS Quantum blog on the hardware device that they are building, for example, but also with advanced cases of optimization problems that they work with, and that's public. Now, in terms of learning quantum computing, probably a very good way to start is those notebooks that I was showing earlier. You have a whole folder structure that is also available in GitHub. You don't need to launch spin up a notebook instance or anything like that. You can just download those examples from the GitHub repository. And from the very getting started, analyzing the device structure to start building your first circuit and do more complex thing in an accumulated manner in terms of complexity, that's a great resource to learn. At least it was very useful for me.
And I did find those and put those examples that were on the GitHub for the AWS GitHub into the chat, so the audience can go out and take a look at those as well. So hopefully that'll get JibJab 06 kind of started there and learning some things. Also an interesting discussion, not related to today's topic, a little bit about cryptography in the chat here online, but we'll keep it in the chat there for today. Otherwise, I think, Juan, I'll let you continue on through some more of your content, but I appreciate all the insights and info so far. It's been really interesting.
Thank you, Rob. Let's dive into more stuff. Let's start talking a bit about security, right? That's the initial purpose of the session. Yeah, as I said, I want to use identity and access management as an excuse to talk to you about the different services that Amazon Braket interact with. So here I pasted a window of IAM user creation. And this is probably the first thing that I have to say. And even if it's the same for every other AWS service, I want to make sure for the people who are probably experienced in quantum, but not so much in cloud, need to know. You create an IAM user and you give to that user the actual permissions and policies that they need to do the tasks that they are meant to do, but nothing more than that. On that sense, the Amazon Braket full access policy, it contains everything that is required to run the service safely. All those interactions that you saw before on the right-hand side with S3 and so on are covered here, so you are able to run your notebooks and store your results and all that in a safe manner. Now, it's also possible that you are a very mature organization that, or maybe you don't like the actual graphical interface, or your company does not allow that. And it's totally okay to create a user that is just an access key for programmatic access and will not have access to the console, but everything in AWS is an API. So it's totally okay to configure your local environment and using the Braket SDK, start interacting with the service that way. We published a blog on how to do that. So you can follow that blog step by step. We will put the link there for you to follow and access the service that way. Now, what is inside this Amazon Braket full access? I'm not going to cover every single service that it has, but some of the most important services. Number one, as you saw, Amazon Simple Storage Service, or S3 for short. There, the experiments are stored. The results of your experiments are stored, and you can read from there all the detailed information about your task. It's restricted to a specific bucket name that starts with Amazon-Braket, so nothing else within the S3 service will be able to access by your user, only the buckets that are called with that specific prefix. Then you have the Elastic Container Registry. With ECR, it's used for the hybrid jobs feature of Amazon Braket. It's a feature that we didn't have time to touch on today, but basically allows you to run hybrid workloads of classical computation with quantum computation. We have a partnership with a company called Xanadu that produces a set of libraries known as Pennyline, which is a software framework and allows you to basically run your quantum machine learning type of problems or algorithms using familiar tools like PyTorch or TensorFlow. So with this container, you are able to, or with hybrid jobs, you are able to basically use the predefined containers from Pennyline in order to build these mixed or hybrid algorithms within the service. And Braket has access to that as part of this policy. Then CloudTrade logs, obviously, because everything that the users do needs to be recorded and can be monitored and tracked. So for each specific user, you will be able to see when they access to devices, what did they do on those devices, the tasks that they launched, and which type of quantum computer or simulator were used, and search for your tasks when you have a lot of them, and so on. Then SageMaker, it's a very important service for us. We work very closely with this service because all the notebooks are based in SageMaker notebooks. You could tell that a Braket managed notebook is a custom version of an Amazon SageMaker notebook. It is where all your code runs if you want to use this option. And we will see later how you can use it in different ways to access your devices and your endpoints, basically. Very good. The next thing I want to do is to discuss a few use cases that customers ask about, and I think they could be very interesting for you if you are thinking of implementing a private environment. But before I get into that, I'll stop once again in case there's any question. Rob.
Hey, Juan, thanks for kind of going over some additional information there and stuff. So I saw we had a couple different services that we integrate with, and kind of just in regards to some of the integration items that are there. So the regular SageMaker notebooks, and there was S3. I think we had involved an ECR integration. Do we support like bringing your own containers, or do you have to use the ones that are provided and everything with the service as we are kind of looking at things?
Yeah, great question. Yeah, we do support bring your own container. So we provide 3 options, the basic one, and then the 2 integrations with PennyLane. But if you have, for example, a simulator that you like a lot, and you want to use that one, that's probably the most common use case that I've seen. You can build your own container with that simulator inside, and then just register it in the ECR service and make it available for Braket. So you just need to specify the right parameters for the service to find the container number 1, and then where to start to execute your code number 2. And with that, yeah, it's available. So thank you for the question.
Great. No, thanks. And audience, please make sure to post your questions in the chat here. I want to let you continue on through here, but we look forward to hearing from you all.
Awesome. All right. So let's start talking about private development, private environments in Amazon Braket. So as you've seen, the QPUs are in different regions, right? You have US West 1, US East 1, and so on. So if you are trying to connect to Amazon Braket in a private way, you don't want your traffic to traverse the internet. For some time now, Amazon Braket offers private link. So that means that you can create a private endpoint with Amazon Braket and then configure your development environment, if you already have one, to point to the private endpoint of Braket and write your code without having to traverse the internet, right? Now, one thing that you need to take into consideration is that this setup works by default or out of the box, as you can see on that picture, just by creating a VPC endpoint for my Braket, and also a VCP endpoint for my S3, because my results, as you see, they need to be stored in a bucket. So you need a private endpoint for S3 as well. You will be able to access to every device that is in the same region that you are trying to operate in. So if I'm in US East 1 and my QPU or quantum processing unit is in US East 1, then that works out of the box. But what happens if I am in a region and I want to access to a device that is in a different region, but I still don't want to go through the internet? Or even worse, or better, I have my development environment in a place where there is no Amazon Braket at all. I just want to spin up a SageMaker notebook and maybe configure the right packages with the SDK and all that, and access to that device in another region. Well, that's possible as well. We published recently a blog that explains how to do that, all the steps that you need to take. And basically, you can leverage the feature of VPC peering between regions and private link within the region in order to build this environment. You will be providing private endpoints for Amazon Braket and S3, and then in the region where you are trying to connect from, or where your development environment is located, you will have also your private endpoint for S3, because you need to put all your packages for your notebook to read from there. And there's some special things that you need to do about the routing in order to make this configuration to work. One of them is the DNS resolution. You will need to use Route 53 for that. But maybe better than me talking over this picture, we could jump into a demo where I show you how all this thing is configured, and hopefully that will help you to get started in combination with the blog that we're going to give you the link for as well. Let's jump into the console, and I'll show you how that's configured. Here you can see VPC console for US East 1. This is where one of my QPUs are located. And what I'm going to do is to go to VPCs, first of all, and show you what I built there. You see a VPC that I tag as Braket that is configured in the 10.10.00/16 mask and network. And that's going to be my QPU region, if you want to call it that way. From here, we can go to the subnets. We have two subnets inside, .1, and let me sort this out first by name, .1 and .2, just for high availability purposes, no more than that. But that's my CIDR. We can check the other one as well, so you see the details. Let me click on that, and that's the 10.10.20/24. So those are my subnets. Then the routing is the next part that is kind of important here. As you can see in this Braket route, I have two routes. One of them is the local traffic for my 10.10.00 network, all good so far. And then you see another CIDR that is a 10.20 CIDR that is being routed to this peering connection. That's what PCX means. So everything that comes from that network or from that subnet, those subnets, it's going to go to the peered connection. Let's take a look to that peering connection here in USTS1. So what I'm doing here is to basically interconnect two VPCs that are in different regions. My other region in this example is in Ireland, in US West 1. And as you can see in that window, there is a requester and an acceptor. That's the requester CIDR, that is my local network, is in USTS1. And then the acceptor one is in 10.20, and it's in Ireland. So what I did is to create this peering connection and ask Ireland to accept it. And that's what you can see here. And I'm routing my traffic that way. Now, the next thing that you need to do is to create the actual endpoints. There's two endpoints, one for S3 and another one for Braket. Let's go ahead and take a look to the Braket one first. So you can see the DNS name is a private name there. And from here, the most interesting thing is to check these DNS names enabled and leave it unticked. So no DNS within this endpoint. Why is that? Because if you enable DNS at this level, you will not be able to route traffic that comes from the other region, even though you are peering two networks and everything is linked. The other network will not be able to route traffic at the DNS level to this one. So to go around that, you need to do the routing in a different way, which is using a global service, right? Like Route 53. Here you have the rest of the details. You can see that the actual DNS names are private. This is the S3 endpoint, just configured in the same way. This time is a gateway type of endpoint, but the rest of the configuration is identical with no DNS resolution. And then probably, yeah, I think I can show you Route 53 and how the actual DNS routing is doing to finish on this part. I go to the console. The first thing you notice is that this is a global service, so I don't depend on any regions anymore because I'm in Route 53. And I created a hosted zone here with the name for the service, for Braket, that is going to connect to, is going to route traffic to it. I'm pointing my A record to my private endpoint that I created previously. And that's how this routing works. No matter where the traffic comes from this region, from one region or another, everything that comes to that endpoint with that record name will be routed at the DNS level to my private endpoint. And that's how this is configured. Once you have done all this in your QPU region, the region where Braket runs and where you have your quantum processing units, you can go ahead and do the work in your actual development environment. The first thing I'm going to do is to change to VPC. So I go back to the regional scope, and then I'm going to change region to Ireland, which is where I have my development environment. Here, let's take a look to the VPC first of all, and you're going to see the mirror configuration. As you can see here, you have the 1020 CIDR. It's important that CIDRs do not overlap, okay, between the two regions, so otherwise it won't work. And these are my subnets, 21 and 22 in this case, that I tagged there as quantum development environment. My route tables, this time is the opposite configuration. So everything that is 1020 is routed locally, and everything that goes to the 1010 network that is on the other side, it will go to the actual peering connection. And if we click on the peering connection, or here on the left-hand side, you can access to it as well, you can see that the configuration is identical. The requester ID is 1010 from US East 1, and the acceptor CIDR is 1020, located locally here in Ireland in this case. The configuration endpoint, you have to do it just for Braket. And in this case, it's just an endpoint that doesn't have DNS enabled either, as you saw in the previous example. All right, the next thing I'm going to do is to go to SageMaker to finish with the configuration on the local side. And here there's no Amazon Braket, right? Because Amazon Braket is not available in Ireland. So what do? Well, we configure a notebook instance in SageMaker and configure it as if it was an Amazon Braket instance. I launch it here, an instance, and what I did is to create a notebook and configure everything to make it work. So you can see a list of packages there for the Braket SDK, and also install the Penny Lane libraries that I was mentioning earlier for quantum machine learning. I put them as well in this machine. So when I start to import libraries and things like that, it behaves like an Amazon Braket notebook. The imports I have to do are a little bit, they're a little bit different, but the only thing that is extra here is to import my Boto libraries, because I have to specify, and this is important, the region that I am connecting to when I define the device. As you see there in the second cell, let me execute the first one first. And there in the second cell, you can see that the session is defined by specifying the name of the session in US East 1. That is important because right now I'm in Ireland, and if I don't specify that, even if everything is open from the DNS point of view and routing point of view, I will need to tell my code as well where my QPU is located, my quantum processing unit. And then I pass that parameter to the actual device definition. This is the IonQ device that I showed you earlier, and I'm passing the name of my region. That way, I just can connect to it completely privately. I'm executing a piece of code here just for you to see that this thing works, where I just print the basic information summary about the device. From here, you can go nuts. You can start writing your code, and everything will be working in a private mode without you traversing the internet. All right, let me see how are we doing on time. Perfect. I just wanted to share one more thing before we close it up, which is the question of, okay, what if I want to not only connect from one region to the other? This is my demo that we already did it. Perfect. What if I want to connect not to my QPU region from my local development environment, but I want to be able to use all the Braket endpoints that are at my disposal? Well, you can do that as well. The configuration, the only difference in the configuration is that instead of using VPC peering, that is a one-to-one relationship between two VPCs, you will be using Transit Gateway. That is going to give you that full mesh connectivity from your development environment. You will define everything exactly the same in terms of DNS routing. So remember to deactivate the DNS resolution at the local level in each region. And instead of using VPC peering, you need to use Transit Gateway to configure it. In this case, the advantage is that you will not need to pass the region to the device when you define it anymore, because since everything has connectivity, the Amazon Braket SDK is smart enough to know where the device is located when you define it. If I say IonQ or Rigetti, the SDK will say, okay, I know that's in this region, and I will try to access, and it will work because your networking configuration will be hopefully well configured, and it will have access to it. Those are the things I wanted to share with you. I hope it was informative, and it will unlock you to start working in your quantum development environment. If you already have something that your company uses and you want to start exploring quantum, you don't need to go and go out to the internet or make it any unsecure or anything like that. It's pretty safe and it's well tested. So try it and let me know how it goes. That's all I have, Rob.
Hey, Juan, thanks. Appreciate the information. So I did have a question. Shared the blog in the chat with the audience to take a look. Just curious, as far as, if our audience has any troubles getting, some of the networking configuration setups, is this something AWS support can help them with to get kind of going?
100%. We are in synchronization with them. We test these things together, and they are all very well aware that this environment exists. So if you run into trouble, you can open a support case, and they will be more than happy to help you.
Great, thanks. And I'll post a link for a little bit more information on AWS support there. Just checking, we got a couple minutes. Anything that you wanted to add on just real quickly at the end here?
Maybe my personal advice would be that just get your hands dirty and just jump into it, start writing the code. Maybe at the beginning you don't understand very well what you're doing, but everything start making sense, I guess, as everything else when you start practicing hands on keyboard. So go for it and let us know what you build.
Makes sense. Yeah. So definitely get out there. Of course, we always advocate for being builders. So everyone, today we looked at what quantum computing is and how Amazon Braket is facilitating the access to it. We also analyzed the security aspects of the service and learned how to build a secure development environment using some VPC peering and such. And so thanks for tuning in. I also want to share, if you'd like to see some more AWS content today, stick around for AWS Pi Day. We're celebrating 16 years of innovation with Amazon S3. Starting at 9:30 Pacific, there will be 14 AWS storage sessions, including a keynote from Amazon S3 Vice President Kevin Miller and closing remarks from the AWS Chief Evangelist, Jeff Barr. If there are any questions that were not answered today, you can feel free to post those over on repost.aws. And you can feel free to email us any feedback at awssupportsyou@amazon.com. We do really look forward to hearing from you, and let us know what else you would like to see on the show. We'll also be posting a link to a survey here in the chat. So let us know what you think of the show today. And thank you for joining us at AWS Supports You. Happy cloud computing. And thanks again, Juan, for joining us.
Bye.